Hello everyone, welcome back to This Is Not a Science channel, and this is our second physics video. And this video is a continuation of my previous physics video, which is about mass and weight. So make sure you check out that video before you watch this one, because in this video I'm going to be using materials from the previous one to explain a lot of things. So make sure you watch the previous one and then come back to this one. I'll put the link in the description, so if you haven't watched it, watch that one first and then come back to this one to learn about principle of moments, which is really essential. It's all around our lives, and I think it's a really interesting topic as well. So the words principle of moments might not sound familiar to most of the people, because it's happening all around us, but we rarely spend time to actually understand how it works. So in order to actually understand principle of moments fully, we have to start with smaller concepts and build it up together. So we'll start with center of gravity. Then what is center of gravity? Well, here's a definition of center of gravity. It's a point from which the weight of a body or a system may be considered to act. So basically, if we have an object, a regular shaped object, it's quite easy. We just have to find the midpoint. Just like this one, these two objects right here, their weights are expected to act in the middle. So in physics, in order to make our calculation slightly easier, we will assume that the entire weight of this object acts right at the center, because we all know that this object exerts the force on its entire surface. But in order to simplify, we just simplify it as the center of gravity being right in the middle of a regular object. So in the future, when you see like a regular object, like for example a square or a rectangle, just assume the midpoint as the center of gravity. A little revision right here from the previous video, like the materials from the previous video, because I thought it will be useful for us to remember this. So here's a formula: work done equals F times D. So I just want you to label what these three things mean first. Alright, and I'll check back later. I hope you've labeled this formula. So let's just go through it, right? So the work done is basically energy, and the unit will be joules, which we simplify it as a J, and the F will be force, which the unit is in newtons, and D will be distance, perpendicular distance to the pivot, which will be in meters. Well, when we talk about principle of moments, we must change this formula a little bit. It's still the same. We just have to change the wordings of it to fit this situation. So we'll change it to moment equals Fd, which is basically the same as the previous one, but we're changing work done to moment, and I'll tell you why later. So in moments, our unit will be Newton meters, which is exactly same as a joule, but we'll call it a Newton meter, which we write as Nm. And the reason why we call it Newton meter is because the force has its unit in newtons and the distance has its unit in meters. So Newton times meter, which is Newton meter. So we simplify moments unit as Newton meter. So this is the version of the formula now you have to remember for principle of moments, and I'll explain why is this. Why don't we just give it a go at some questions straight away based on the formula we have from before. Let's just try to work out. So you got two scenarios here, two seesaws, and they have the same object, alright, but then they're placed different distance to the pivot. So my question now is, which one has a larger moment? So pause the video for now and drop down some ideas, do some calculations, come up with an answer, and tell me which one has a larger moment. Alright, I hope you worked out which one has a larger moment. Well, let's take it step by step. Let's start with the calculation with the left scenario. So moment equals Fd, that's the formula we have to use. So moment will equal to 10 newtons times 0.5 meters, which is the distance from the pivot to the object. 10 times 0.5 give us 5 Newton meters. Alright, let's take a look at the right one. The right one will be moment equals force times distance, same formula. However, it will be 10 times 1 because the distance is 1 meters to the pivot. So that would result in 10 Newton meters. So clearly the right one has more moments. And if you check out my previous video, you'll get it, because we discussed this in the previous video, how when we have a larger distance, we're likely to have a bigger moment if the object is the same. Alright, so we finally arrived at our main theme of this video, principle of moments. And I'm going to be explaining the definition of it and teach you how to actually apply it in real life scenario. Alright, so let's just look at the wordy definition of it. It's not very nice to comprehend, but I'll explain it, don't worry. So the principle of moments states that when a body is balanced, the total clockwise moment about a point equals the total anti-clockwise moment about the same point. So here's the formula we just saw. Moment equals force times perpendicular distance from the pivot. Well, why do we call it perpendicular distance from the pivot? Well, let's just take the previous diagram that we have. If you take a look from the object to the pivot, we got this virtual line of 1 meter. And you can see this 1 meter is actually perpendicular, which is 90 degrees to the pivot, which is represented by this line in the center. So this means whenever we want to calculate a moment of something, we have to use the perpendicular distance from the pivot, which means we have to identify the pivot first of all. And the definition on top, it says when it's balanced, the total clockwise moment about a point equals the total anti-clockwise moment about the same point. It seems complicated, but it really isn't. I'll explain later what this actually means. So in order to simplify that wordy definition before on the previous slide, we have to know how do we actually apply this. So let's just take a seesaw, alright? And if we place a mass on this end, on the right end of the seesaw, well, everyone knows it's going to sink, right? So we'll just call it as we got a force acting downwards, and in this case it's the clockwise force, right? So we got a moment acting clockwise on the right hand side, and on the other side, which we have nothing, we have an anti-clockwise moment acting on the other side, and this means they are not equal. So we can easily call this as they are not in equilibrium. So which basically means anti-clockwise moment did not equal clockwise moment. So we cannot call this equilibrium. So principle of moment basically means if you want to stay in equilibrium, the anti-clockwise moment has to equal to the clockwise moment. I'm going to show you what it actually means to be in equilibrium. So let's just take our seesaw again. Right, so we got this mass on the right hand side just like before, but everyone knows it's going to sink in a clockwise direction. Well, how about let's put another identical mass on the other end of the seesaw. Now the seesaw is balanced because we know it is in equilibrium. The anti-clockwise moment now balances out the clockwise moment, so we can confidently call this system in equilibrium. Well, have you noticed something? There is a pattern with this. So whenever something is in equilibrium, we always call the resultant force as zero. So we got a force acting in the right side and another force on the left side. Well, they balance out, so the overall force will be zero. Another important thing is the sum of the moment must be zero. So we got here clockwise moment. If we call this a positive moment, we got another anti-clockwise moment, which we call a negative moment. A positive plus plus 1 minus 1 will eventually become 0. So let's practice this straight away. Let's use that formula, moment equals force times distance. Let's get straight into a practice. Right, so you see right now, I'll explain the question first before letting you do it. So we got a 10 Newton force right here, alright, and it's 1.5 meters away from the pivot, and we have an unknown force on the left hand side, and from the seesaw we can tell it's in equilibrium. So I want you to calculate for me what is the unknown force. Alright, so just pause the video now and give me an answer later. Alright, I hope you worked out an answer. When you see this diagram, the first thought that must have came in your head it's definitely going to be this system is in equilibrium, because you see the seesaw is not moving. So what does that mean? It means the sum of the moment would be equal to 0. So basically, the left-hand side moment will definitely equal to the right-hand side moment. So let's calculate the right-hand side moment first, which is the clockwise moment. So moment equals force times distance. Moment equals 10 times 1.5 meters, which equals 15 Newton meters. Right, so we know the clockwise moment is 15 Newton meters. However, how do we work out the left side, which is the anti-clockwise moment? Well, we know this system is in equilibrium, so we can confidently say that the left-hand side, which is the anti-clockwise moment, is also 15 Newton meters. So in this case, we can just rearrange the formula with F equals moment over distance, because we're trying to find the force exerted by this unknown object. So we take the moment, which equals to the clockwise moment, which is 15 Newton meters. 15 Newton meters divided by 0.5 meters give us 30 newtons, which is the force. That's the answer. Check if you got the right answer. Congratulations if you did. Let's try another one. So here's another question. In this case, we have two different forces, and we know what their values are, and the unknown this time is the distance. So just give it a go on figuring out what the distance is. This one is actually a trick question, because if you take a look at the two objects, they have different units. So this leads us back to the previous video where we have a different formula. So we need actually two formulas to solve this. So the first formula will be moment equals force times distance, that we know. And we need another one, which is weight equals mass times gravity. So most of you probably forgot about this. Well, he's back, right? This equation is back. It's always going to be around physics because it's really important. So how do we apply this? Well, basically, we see that when we have the clockwise bit, right? The unit is in kilograms. Well, think about it. Is kilogram a unit for force? Well, not really. Kilogram is a unit for mass. And on the left-hand side, we got newtons, which is correct, which is the unit for force. Well, in this case, we have to find out the force on the right-hand side. And if you notice one thing from the previous video, weight has a unit of newtons, which is the exactly same as force, which is also newtons. So what we should do here for the right-hand side is we should start with W equals mg, weight equals mass times gravity acceleration, which is 5 times 10. If you can remember from the previous video, our gravitational acceleration on Earth is always 10 meters per second squared. So we have the force being 5 times 10 equals 50, right? So we can take this force and multiply by the perpendicular distance to the pivot, which is 0.8. So 50 times 0.8 equals 40 Newton meters. And we just have to rearrange the other one with being distance equals moment over force. So distance equals 40 because it's in equilibrium. So the clockwise moment must equal to the anti-clockwise moment. So 40 Newton meters divided by 20 newtons will give you exactly 2 meters. I hope you guys are happy with the definition of principle of moment. This is just a small introduction to it. Next time, in my next physics video, we'll do more practice. We'll do more practice in real life to show how this concept can not only be used on seesaw, but on a lot of different objects around you. So make sure to like the video, subscribe to my channel, share this to all your friends who hate science, and come back next time to discover how we can actually apply principle of moments in real life. Thank you very much. See you next time.